Hey everybody, I'm Jesse. We are talking this week about one pipe, which is um, scalable total order communication in data center networks. So one pipe, it's a protocol that provides causal consistency and total ordering. One of the things I would like us to discuss later is whether that meets the definition of sequential consistency, or if there's some subtlety that I'm missing there, because they don't mention sequential consistency in the paper. Anyway, they do provide these two guarantees, and they do it with much, much lower latency than the usual protocols we would see that achieve this consistency level. It's called this because it metaphorically provides one pipe which connects all senders to all receivers with first in, first out semantics. So the application experience is like every message that you send just gets stuck into the beginning of a pipe that orders all of the other messages in the system, and then every message you receive also comes out of this one pipe. Obviously, the actual implementation uses all of the available paths through the network because one pipe would not actually be scalable. Besides these total ordering and causal consistency guarantees, it also has a neat feature called a scattering, where one node can send messages to many other nodes. It's like multicast, but messages in a scattering share a positioning in the total order. So they all have the same timestamp, but they can have different contents and different recipients. And they are delivered atomically, meaning either all recipients receive the messages in the scattering or none do, but that's only guaranteed if there's no crash. Not the recipient, the sender, the switches in between, none of them can crash. If so, then we get this atomic delivery. And it's got two versions, either best effort, which requires a single message delay, so that's half of a round trip delay, or it's got a reliable protocol, and that requires 1.5 RTTs. And we'll look at both of those in detail in a minute. The big caveat to this thing is that it only works in a data center network. So it's designed for the private network of a single organization where they control everything. That's because all of the switches and all of the servers in the network, they all have to implement the protocol logic. It doesn't layer over something like TCP/IP. The network topology must be a directed acyclic graph between any pair of nodes. So you can't have any loops, unlike the internet. I'm a little foggy on this. There's something about how the internet routes packets compared to a data center network that I don't know the details about, but this is the claim. Works in a data center, not on the internet. And it requires extremely tightly synchronized clocks down to microseconds. It requires this for the sake of performance, though it's not required for correctness. So the data center network topology that they describe is called a multi-root tree topology. So I found this diagram kind of confusing, but imagine that you split every node into two. So these two boxes are actually the same node. You're just representing the sender character of the node as distinct from the receiver character of the node. That means that if you kind of slice the network in half and spread it out like this, it's a directed acyclic graph, and all messages always flow from left to right, never in the other direction. I found this other diagram, which I found much clearer in a 2008 paper of a multi-root tree topology. So you can see it has two roots. Messages between pairs of nodes, they have to go up until they find a common parent of the sender and recipient, and then they can go back down the network to the recipient. There are no cycles, but you can see that there are multiple paths. Any pair of nodes that want to exchange messages could use one of the routes or the other of the routes. So there are multiple paths, but there are no loops. And the claim is that as long as you have a network like this, then that makes the one pipe protocol safe. But like I said, I'm a little confused about that. Okay, so let's work through an example of how the one pipe protocol works. I'm going to show you a scenario, and this is like a scenario in the paper, but I've added a node so that we can work through it in more detail, and I'm inventing some details for a use case. And this has helped me understand the protocol a little bit better. So there's 4 nodes. One is an SMTP server, so let's say it receives emails, and it's connected to a storage node. So when it gets an email, it sends the email content to the storage node, which stores the email. Concurrently, without waiting for an ACK, it also sends a new email notification via a switch to a email UI server, which is displaying some like Gmail kind of UI. When the email UI server gets this notification, that means it should request the contents of the email. And when it gets the contents of the email, then it can update the UI. So that's like the scenario that we're going to work through. And there's the opportunity for a causal violation since node 0 sends 2 messages at once. Node 3 could request the email content before it's available, being a causal violation. So it could receive a new email notification, but then when it checks for that email, it's not there. So let's see how one pipe prevents this inconsistency. All right. So once again, the email arrives at the SMTP server. It sends a unacknowledged message, and it uses its local clock. These are tightly synchronized local clocks. And it sets the timestamp to its local clock value. Let's say that's timestamp 1. It also sets this barrier value, which we'll see how that's used. And then the payload is the email body. Concurrently, maybe its clock increments to 2 now, and it sends the new email notification to the switch. And let's say that the first message is delayed, but the second message arrives. So at the switch is keeping track of all of the timestamps it sees on all of the links that touch it. So the default value is 0. So the node 3 barrier value is 0. But on the node 0 link, it's got a message with timestamp 2. So the barrier is 2. And what this barrier means is it's the oldest timestamp that this switch will ever see over this link. So from this point forward, it will never see a timestamp less than 2 on its link with node 0. That's what the barrier means. It forwards that timestamp on to node 3. Notice that the barrier value here is 0. The switch's outgoing barrier value is the minimum of all of its incoming barrier values, because it could forward a message with any timestamp from 0 on up, because it could still receive a message with timestamp 0 or greater on any of its links. So the outgoing barrier value is the minimum of the incoming ones. All right. Node 3 receives it. Its barrier values are still 0. And it now requests the contents of the email, and it uses its local clock, which now is 3, to make this request. And node 1 receives the request. And so its barrier values are 0 and 3, because it still hasn't received anything from node 0. So far, so good. Here we are at the moment of the causal violation, where node 1 has received basically a message from the future, and it doesn't yet have the information to answer it. So how does OnePipe prevent this? OnePipe's rule is no message is, quote, delivered to the application if its timestamp is less than the barrier. So in this case, node 1, it receives this request, but it doesn't actually act on it. It just enqueues it because the min barrier is less than the message timestamp. So this node is not yet caught up in the timeline to the moment where it's allowed to act on this message. So what happens now? Let's say that this delayed message is finally delivered. So now the barrier value for node 0 is 1. The barrier value for 3 is 3. The storage node is allowed to act on this message, and it stores the email. Is it ready to respond now to the request? It actually isn't yet because its barrier value is still 1, and this request timestamp is 3. So node 1 isn't caught up. And the logic here is node 1 could still receive another message with timestamp 1 or a message with timestamp 2, right? Because those could still arrive from node 0. We don't know if node 0 is done sending messages with lower timestamps. So that's why we're not allowed to process this timestamp 3 message yet. At least this is my understanding. What do we have to wait for? We have to wait for some other message from node 0 that's going to increase its barrier value up to 3. That could be some other application message, or after a timeout, node 0 will send a beacon. Any link that's idle for more than a few microseconds gets beacons sent along in order to kind of keep the crank turning. So let's say now the clock is 4. So it sends a beacon with timestamp 4. The minimum barrier value at node 1 is now 3. So we can deliver this message and act on it and reply. So that is how OnePipe ensures causal consistency using these barrier timestamps. I seem to have duplicated this slide. So I'm just gonna, okay. OnePipe provides 2 reliability levels. Best ever OnePipe is what we just saw, where nodes send messages without waiting for acknowledgements. So they can be highly pipelined and achieve very high throughput because they're never waiting for acknowledgement before they send the next message. You get at most once delivery. Packet loss is kind of not handled. You get causal consistency and you get total order. There was some discussion of how the application should register a failure handler and deal with packet loss, but I wish that there had been more detail about that. The other reliability level is reliable OnePipe, and this is basically a 2-phase commit protocol. So a node sends prepare messages to all recipients in the scattering until the recipients acknowledge them. It delivers these prepare messages directly, ignoring barrier timestamps. So there's no causal enforcement in this phase. Once all of the acknowledgements have been received, then you send commit messages using best effort OnePipe. And so there's no acknowledgement and there is causal consistency in this second phase. But again, how reliable is it? What is the failure handling mechanism? I read the section titled failure handling a couple of times and I still can't totally picture it. So I'd like to discuss that if other people understand it. My evaluation of this paper, it seems fast. It seems much faster than other protocols for achieving causal and totally ordered communication, what the paper refers to as KTOX. Mainly because it is enforcing causal consistency with no round trips at all, which seems much different from other protocols that I'm familiar with. It seems to provide sequential consistency according to the Jepson definition, although maybe that's different because they don't mention it. It has very high requirements. It can only run in a specialized environment. You have to run its protocol code on every switch and every node. It requires a certain kind of network topology. It requires extremely tight clock synchronization to achieve the kind of performance that they claim. And it sort of requires the absence of failures, since it seems like failure handling is up to the application and it's super complicated. What I'm curious about is, if there are failures, can you define a failure handler that would guarantee KTOX in the presence of failures? And is it really fair to compare OnePipe's performance to other protocols where failure handling is baked in? So there's this paragraph that in fault-tolerant applications, OnePipe provides a fast path in normal cases and falls back to the application for customized failure handling. More concretely, an application may use state machine replication to replicate its states and register a fail callback, which invokes a traditional consensus algorithm. Those two footnotes are Paxos and Raft. Each message is scattered to all replicas, so it's sent all at once, not via the primary, but the client directly to all the secondaries. When failure occurs, message delivery is stalled, and OnePipe invokes the callbacks in all non-fail processes. This seems to suggest some sort of coordination, some kind of like stop the world. And I don't understand how it's going to achieve that in a distributed system. It seems kind of like the distributed snapshot problem. It says restricted failure atomicity ensures that all correct replicas deliver the same sequence of messages. If the correct replicas reach a quorum, the callbacks return and the message delivery is resumed. Again, how is it resumed? How are we flipping states between normal mode and failure mode? Otherwise, there are too many failed replicas, and the application can choose between consistency and availability. If it chooses consistency and waits for some replicas to recover, the recovered replicas can deliver the same sequence of messages. I don't know how this works. It seems to rely on some fault-tolerant coordinator that's like outside the system and has some godlike view and never fails. I would like to know more about that. But in conclusion, it does seem like a really cool protocol, and it's useful for high-performance applications in state-of-the-art data centers with modern clock synchronization, and it seems like you can do things that are sort of like Raft or sort of like distributed transactions with fewer round trips. And that is that.